Alright, so the first section that I want to be talking about is router design. And part of that router design deals with the router architecture. How is the router physically designed? And it's broken up into two specific parts, a data plane and a control plane. The data plane focuses on moving the data, i.e. the packets. Also, how do those packets get forwarded? Next is the control plane, which is how does the routing protocol establish routes? How do they communicate with other routers? How do they do the path selection? One of the big things when we're talking about designing some of the larger, faster routers, which we're going to be calling our CRSs, i.e. those are going to be our service provider routers, we're looking at things like speed, power, physical size, the components, the algorithms that they use to look up and process, packet queuing, and switching. All of these are major considerations when we're talking about these. When we talk about size, we're talking very large. When we're talking about price, these are like $500,000 plus per router type costs. So generically, our general architecture is we have some form of lookup, update, and then query. So here our data comes in with the header, gets looked, has an IP address lookup. That address is looked up through the address table. Normally it's in memory. From there, the next hop is returned from the address table to the address lookup. From there, it gets sent to the update header. From there, the queue packet. From there, it gets ready to be sent out. Then the memory buffer actually sends the data to the queue to be sent out. And that's it. So what makes up a router? Major things that make up a router is going to be the interfaces, both input and output, the switching fabric. Our fabric here is just moving packets from input to output and the process that it goes through. Also, the software and features that are used. If we're dealing with a router, we're dealing with the routing functionality or the routing feature of the device, packet processing, scheduling, queuing. Those are all major areas. So what makes a router a router? Basically, routers gets packets. They will look at the header information for the destination, then it will find the information where to send it. It may or may not modify the header depending. Then it actually processes the packet to an out interface, and then it will be sent to a queue. It will actually be then processed and sent out that interface. Interesting thing here is part of that is for the packet modification or the header modification, we look at things like the time to live, the TTL, or sometimes the IP header checksum. If we're updating address information, we have to do a new checksum. That may entail updating our header. So our first generation of routers, everything was on a shared bus. Our CPU, our memory, nothing was really off-chip. What I mean by off-chip is we had a specific plane for our CPU, our routing table, and our memory. From there, part of that shared bus, we had our line interfaces. Those would be our actual physical ports. With this, we're talking maybe a half a gig or 500 megs a second for bandwidth. Information would come in through a line, get sent to the memory bus, and would be processed and sent out to another line. So again, remember, these are 500 megs or less. So how does this stack up against our current CRS type routers? Alright, so here we're looking at, on the left, a Cisco CRS1 versus a Juniper M320. Both are around half a million, easily. The Juniper is smaller in size, however, it has a lot slower capacity. The CRS, 6 feet tall, 19 inches wide, 2 feet deep. It weighs about half a ton. That's over 1,000 pounds, but it has the capacity to process a terabit of information per second, though it uses 10.4 kilowatts, versus again our Juniper model, which is 320 gigabits per second at a nice reduction in power of 3.1 kilowatts. So these are pretty hefty items. And again, these are ISP type routers. This isn't something that a normal business would have. This is going to be a large business. So within that, we have them very modular, which means we could add cards depending on our needs. So if we need fiber, if we need InfraBand, we could add and remove items as we need. For example, our Juniper add-on card here, it was an M40 add-on card. It was a 1-port OC48 slot, or basically a add-on card that would allow it to process 2.5 gigabits a second for a OC48 line. While the bottom right, that is a 4-port 10 gig E switch for what looks like LC fiber. The nice thing with these routers are they are fully customizable. All depends on your environment, and they will shift depending on your needs. So here's normally where we get asked the question, so we have big fast routers, but why bother with them? Because we have faster links, we need a way to use them, to utilize them. Because we have bigger links or faster links, we need larger routers. It's an increase in demand. A gigabit used to be sufficient. Now it's not. We have a much larger increase in demand with our cloud services, our VoIP technology, 10 gig dropping in price dramatically. So we need equipment that can handle this. Larger sizes. That's a big one. Larger networks are becoming more and more commonplace. And it's not always a large network centralized. It could be a large network that's spanned. Also, these larger, bigger routers are more cost effective. So we already talked about our first generation. But again, this is the important part. We're talking about less than a gigabit per second for speed. Benefits with these newer, faster routers is each inline card has direct access to that shared bus, and thus allows each to have its own routing table. What that really allows, though, is not allowing the one routing table to become a bottleneck for processing information. However, one of the major complications is updates are sent on the fly, and that means updates for these tables happen pretty quickly. A big part here is dealing with our BGP tables. Part of that BGP table actually is dealing with our forwarding information base, and that's going to be our more specific addressing. We have a PowerPoint that's going to cover this portion here in a little bit, so I'm not going to dive too deep. Again, going back to our generic router architecture, it gets sent in, it gets the header to be processed, and it will go through this data process. And the correct information is sent to where it needs to go, or it may be looked at an address table before being sent out. The nice thing with the second generation is forwarding cache and larger memory buffers per inline card. So one of the issues was when we're having to rely on just the system's memory, it was slow. And that was a major thing, was the CPU was being bottlenecked. Okay, it would go in, it'd be forwarded to a cache to its memory buffer, and instead of having to go to the system's memory buffer, it could be sent directly out the physical interface that it needed to go, completely bypassing the CPU and completely bypassing the memory, which allows us to transfer data quicker, and then out, of course. One of the nice things here is cache bits for forwarding tables and line cards no longer had to be interrupting the CPU or system memory. We also had faster shared bus pathways, which again allowed for faster communication. Basically, every input port has a connection to every output port, and that allows for faster data to be sent. However, one of the major issues, we're talking about pathways, and they can be exploited, so that's a major issue. One of the nice things, though, is within a time slot, they actually zero out all of their connections other than the active one being used. It also exploits parallelism. That means if a data frame had to go to multiple interfaces, it's a lot easier to do. For example, if A was going to communicate with Z, Y, X, it wouldn't have to do a dedicated pathway to Z, a dedicated pathway to Y, dedicated to X. It'd be allowed to send on all three ports, and it would just zero out the connections for B and C. However, this means something has to be in charge for scheduling. So our third generation of routers was allowed a periodic control update. This crossbar switch plane actually allowed for almost 100-fold increase. So going from 500 megs to 50 gigabits per second. And again, it would be sent up a physical port to our switched backplane, or our crossbar backplane, and then it would be simultaneously allowed to be sent out individual ports, or multiple ports depending. So we keep saying this backplane, but what exactly does that backplane sit at? How does it work? These are fairly old information, but it basically operated at a OC768 line, which is 40 gigabits per second, and this is old. I know newer connections are 50, not 100 gigabits per second for their backplane. And again, that's just communication between cards. And that also means dealing with large amounts of packets. I'm looking at the second bullet point, which is had to be able to process 40 billion packets per second, or that's 8 nanoseconds per packet, and that's processed, sent, all of it. And that also is calculated in with error. So it's not 40 billion excluding error, no, it's 40 billion including error. The nice thing here is because we had to deal with scheduling We had things like QoS and filtering abilities. Filtering, of course, by ACL, but we had the ability to filter. So how does this crossbar mentality actually work? Here is the less complicated way that I was able to find it, which is basically a time slot. That's a big thing, is maximum matching. It looks to see where it can send out information, and then it will actually schedule time to be sent out to that specific port. So here we have 3 inputs, 3 outputs. Simultaneously. I mean, again, input 1 had 3 bits, and is able to be sent out 3 individual outputs. It's all about quicker access, quick. Because again, these are ISP-based routers, so we're talking about high bandwidth. Some of the advantages to this input-output queuing is it's really easy to build, it has really good throughput. However, it's harder to design our algorithm, and it does allow for congestion points. That was a big thing. Here we look at virtual queues. That way we could be queuing up line items a different way. The issue with that type, though, is we have like speed and fairness. Fairness in the sense of packets of information and how they're treated. There were alternatives to the wavefront scheduler, and that was a parallel. Though the parallel matching may not always be maximum, and it would run several times. So we're talking about additional overhead. We also had round robin, and so just because we look at one way doesn't mean that's the only way, or doesn't mean it's the best way, because there's always multiple ways here. Scheduling and fairness, this is a big one, because scheduling the information to be sent out queued so that it will be sent out in a timely manner is extremely important, especially once we start putting weight on them. Weight is in QoS. That way we can guarantee a specific protocol additional overhead or additional bandwidth regardless of overhead. And we try to match those promises. We have a max-min fairness. Again, we have several different types of fairness. I'm not going to go into detail about each one. You guys are capable of looking into them. But know that there are different types of fairnesses used for calculations for these higher-end routers. Okay, so let's look at some of the challenges. For our IP address lookup, we're talking about prefixes that don't match, tables that are growing too large, and that also means our lookups have to be faster and faster and faster. Here's an example of a long prefix, 192.16 or 128.9.16.14. Assuming a subnet mask of what? Assuming a subnet mask of /16, 128.9.0.0, that would have to be queued. If we're looking at a subnet mask of 255.255.255.0, we could, or /24, I apologize, would be looking at the first 3 octets as network, the fourth one being our hosts. We could even fine tune that even more if we go a /28 using the first network, so that would be 16.0 through 16.15 for the first network, so 1 through 14 usable. It really all depends on the prefix. Which one are we calculating based off of? Okay, that's a huge thing. Here our routing lookup finds the longest match, which should be, they did a /21, which Yes and no. I mean, it works, but other ways to do that. All the prefixes will match, so that's a good address. But we'll run the calculations to find the appropriate prefix. The tables are growing large, and they're still increasing. Here are our active BGP entries. And again, this is only the 2010, and these tables are huge. San Francisco, I do believe, has a BGP AS table that you can that anyone is allowed to look at. And I mean, it takes like a good 15 to 16 minutes for the data to load. Last, lookup tables got to be fast. That's one of the main challenges. So, what do we mean by lookups have to be fast? So our line cards in early 90s, we were getting away with, you know, a half a gig, a 2 gig. But in 2001, no. That was no longer fast enough. We needed 10 gig. 2003, 40 gig. Now, 2015, it's a lot more than 40 gigs. The specific number, I keep getting varying information, so I'm not quite sure, but I would not be surprised if it's not 100 plus gig, if not larger. So how does the address lookup portion actually work? So it looks through this type of binary tree. And what it does is it looks at the first groupings of 1s and 0s, and then it goes down a pathway. If it's 0 or 1, if it's 0 it goes to the left. Once it goes to the left, it looks at the second pathway, then the third pathway, then the fourth pathway. Same thing on the right. If it starts with a 1, then it splits off to 2. Is it 1 or 0? Then again, it just starts going back over as it slowly starts looking at the entire binary number. It's slow. That's the big thing, is this type of directional method is slow. It's also very inefficient use of memory. That's one of the alternatives, is going to be our CAM, our Content Addressable Memory. It's basically hardware-based route lookups. And that is a tag versus a value. It's faster. It's more efficient within memory. That's the big thing here. However, our CAMs are not always very economical. So that's another consideration we have to think about. We also have caching, or what is more common, our Cisco Express forwarding. That's a big one, is you want to know our Cisco Express forwarding. And that's the beginning of our introductory to routing architecture. So the next chapter is all about CRSs. Again, a CRS is a very high-end router. It's really hard to explain if you've never seen one, but I mean, these guys are massive. They're flexible, they have a very specific fabric, and the interesting thing is they're very modular. Again, with line cards, the line cards can be several $1,000s, but I mean, they can do a very specific task, or they can do they can have several different tasks assigned to them. It just kind of depends on the type of line card that you need. That's what I mean by they're very modular. So what drove Cisco to do the CRSs? A big part of that was our higher end OC lines. That would be an OC768 or larger. The fact that they were tired of doing a single type chassis, so they needed a multi-chassis unit for additional support. Big thing is bandwidth versus watts, and bandwidth versus space. These guys are massive. I mean, with how large they are, you need an extra special amount of power, and you need an extra special just amount of space to house one of these guys. So they wanted to make sure that they were getting enough bandwidth for the power and space. Next was because of all the new feature sets, you also had to look at a new operating system, hence the iOS XR. After that, it was a scalable control plane. With how big these guys were, they needed a way to grow. Again, this unit is $500,000, so you have to keep that in mind. These are, again, a core router, and normally used for at least high-end OC lines. We're talking a half a gig, if not larger. An OC 768 is a 40 gigabits per second line. They are expensive. That's a big thing. The high-end one allows you to support 1.2 terabits per second. One of the interesting things here is the interconnect up to 72, meaning you can interconnect multiple CSRs so that they can distribute the load across one another, allowing for a bandwidth of up to 92 terabits per terabits per second, and each one of them starting at about 500,000. These guys are flexible, but they again are extremely expensive. They are customer facing. They do allow for frame relay and ATM, but they also do a very specific queue set. For their transit / pure facing, you can do OC lines, gigabit. It has full BGP support, full ACL support. Interesting thing here for BGP, that's iBGP and eBGP, so both internal and external routing protocols. It also does AAA, the authentication, authorization, and accounting. This is really a all-in-one unit, but again, you're paying for it. You're paying a lot of money for it. Over time, routers have been pushed to the edge. A big part of that is bandwidth. Also, the higher-end routers with higher-end port capacity, they have fewer ports, or have to have the ability to come with fewer ports and grow as needed to help reduce costs. Different routers have different offerings. Most times it's all Ethernet based, but it kind of just depends on your environment. Again, it's heavily redundant. You can have multiple of these in tangent working with one another, multiple power supplies, multiple control planes, multiple everything, so that once this unit is up and running, you don't have to worry about it coming down. If these guys are coming down, that's because of a larger issue. So what exactly does scaling mean? Scaling means you can scale or increase on the fly interface, that's bandwidth, the number of ports, the various types of ports, gigabit, copper, fiber optic, anything. It supports a faster processor, which allows for more routes. Hence, think core layer of the internet. A better management, a better ecosystem, faster control, which means faster processing of our packets. It's available. It's really funny that when you say it's available, but I mean it's made for high availability. If a portion of this unit goes down, it can still function. It can scale up and down depending on the system that you need. It's serviceable, which means, again, with how modular it is, you could run with like a quarter of the unit there. So it's, if you need to work on it while it's live, you can move everything to line cards that will be up and running, so you can work on the down line cards. Then as you get done with them, you just slowly migrate the load over so you can work on the next set. Low bandwidth feature rich, and it's centralized. Again, it goes back to that shared bus. Again, the CPU and memory are on the shared bus. Off chip, same thing. Nice thing here is again that crossbar, because the crossbar allows for higher bandwidth equals better distribution, which means multiple line cards and multiple ports can function together, faster speeds. That also means simultaneous routing. Hardware-wise, the switch fabric is actually faster. We're talking milliseconds delays between the units. You allow for higher bandwidth switching, better QoS, better traffic control, better decision making. All of this goes with a more limited amount of resources, but more efficiency. If you had to display or describe the control plane in a few words, we're talking high event rate, which means it can go over and over and over new events at a very high rate, regardless of if it's queuing, if it's path selection, path forwarding, encapsulating. It has a very high or extremely high event rate. So that fabric shelf allows it to talk to other units with its out-of-band gigabit control bus fast, which means it can work in tangent with other units. So how are the CRSs designed? Essentially, we're looking at, per line card, about 40 gigabits of data throughput per line card. And you can do in tangent 1100 line cards. So that's 1100 times 40 gigs, all because of the way that the fabric functions. Talk about amazing bandwidth. It's scalable, it's fast, it has minimal disruption with QoS modeling, blocking, balancing, and redundancy, which we've already discussed. But let's get into the nitty-gritty. How exactly does this thing work? Internally, this is how it kind of functions. It uses a cell-based multi-stage bins. It basically allows for a multipath to destination. Each one has multipath switching internal to the router. That way, switching can take multiple pathways, thus allowing faster speeds. That CRS fabric allows for up to 5 times the typical speed. That's been a huge thing. Discards. The time constant in tens. We're talking milliseconds. Back pressure, same thing. The fabric is not overly loaded, and it can scale easily. What I really liked here is the reassembly window, which allows for cell transitioning between the fabrics. They can take different paths, and thus get to the endpoint or the memory quicker, thus allowing for simultaneous putting back together the packets. They can arrive out of order and the unit can still reassemble that I was looking for, even though that slide was named reassemble. So some of the line card challenges are, first of all, cost of ownership. These line cards are expensive. Power. While they have multiple interfaces, they also have a complex CPU subsystem and memory subsystem, and so there's just a lot here. So how the line card is designed? We have the CPU, we have memory, we have our ingress and egress queuing. Then we have our actual interface module. The mid plate actually separates the module service card from the interface card. Now let's look at it as a real photo. It's a heavy, dense card with lots of resources tied to this. But then again, this is also like $4 or $5 grand per card. Here we have our egress and ingress queues. Notice the additional memory next to our Metro subsystem. But what is it? Our Metro is our massive parallel NP processor. It was designed by both Cisco in conjunction with IBM and Tensila partnerships. But I know Cisco and IBM put a lot of time into this. They actually coordinated with Israel and the HQ in San Jose. These Metros were designed to be programmable and scalable. That was a huge thing, it's very scalable. Another feature for our subset is our TCAMs or our CAMs. Dual channel with additional memory. We also have additional memory for our processors and other Metro subsystems. This allows for, again, 96 gigabits for bandwidth, and our control plane will allow for 2 gigabits per second for proprietary information. But if we're talking about just straight packet switching, 96 gigs of total bandwidth. What about memory bandwidth? It has a 32-bit processor, so it can do around about 50 bits with a memory bandwidth of roughly 175 gigabits per second of memory bandwidth, thus allowing the Metro processor to organize it, process it, queue it, send it out. Memory, the higher density memory and the higher speed memory allows for better processing time. What does it mean by programmable? Big part here is forwarding. How does it look up addressing from the lookup tables and or CAMs? It's all about being able to quickly forward information. Here we go from our CAMs to our RAM to our lookup, and we are looking through millions of routes to find the specific route or pointer to the route so we can queue it and send it off on its way. Here are the feature sets that it supports. The big thing here is MPLS, load balancing, our ACLs, our multicast and unicast, both IPv4 and IPv6, our VPN tunneling using GRE and L2TP, and again, congestion controls, our QoS. Programmable also means the agility to juggle featuring, features and featurings that allow for order or priority services, thus allowing priority to certain queues over others. How does this work though? So a packet comes in, the packet tails are stored on a chip, the actual packet header and packet fabric goes in to be processed. If there is a cost, we can associate with the cost. The packet is distributed. Once it goes to this process, it will actually be allowed to package it, the packet together, combined with our on-chip packet buffer, and then sent out. One of the big things here is everything is done in parallel, so a multi-drop bus is allowed. Some of the resource consists of, again, memory, CPU. Our CPU or algorithms are very heavily mechanized. So let's look at our chip on our Metro. Here's our chip a little more in depth. You can see our Q depth, you can see our statistics, our cams, our tables. Everything that we need is right here. And this is the design of our Metro resource. This is our algorithm for path selection. These are all our processor types, our cluster types. So what was a PPE? A PPE was our packet processing element. That's the portion of the processor that actually allows for the packet processing. It's normally a 5-stage pipeline, and it essentially does small instructional sets. It is only 32-bit right now, but within this, that was all they needed. Again, we've already talked about the programmable of the model, we've already talked about the data points and the efficiencies using this type of system with QoS and our ACLs. We've already covered some of the challenges: power, size, heat, cooling, performance, cost, scalability. Those are all major ones. Our PPEs versus our hardware acceleration. How fast can this unit pump packets out correctly? How well can it perform? How large of a load? What about cooling? What about power consumption with that load? There are just a lot of challenges. Some of the future directions that they're dealing with right now are edge and core differences within different blurs, the smartness within our network, the decrease in resources while still being able to maximize our bandwidth and our scalability. A big part of this is also leveraging our cost feature sets. So in summary, our network growth is pushing our routers to be larger and larger. Okay, so the last section is on our Cisco ASR 1000 solutions. While this is a slightly older PowerPoint, it's still relevant because it goes over the entry-level ASR 1000 series overview. That's the innovation and the solutions they provide. Pretty similar to the CRS series, except they use slightly different units, and they're smaller and cheaper. Again, it's made for high availability. It's made for a mid-range, not high range, not low range, but mid-range, scalable and performance. It allows things for VPNs, IPsec terminations, scanning. It supports the typical 5, 10, 20, 40 gigabit forwarding planes. It supports the state-of-the-art QoS. It's an integrated service controller plus security controller. It's a high-speed medium-scale router. That's one of the big things. The interesting thing with the ASRs is they don't come in a whole 6-foot rack series. These guys come in a 2, 4, 6U array. That also allows for a 3, 8, or 12 slot peripheral edition. That way you can do built-on performance or interfaces. For example, the 2U supplies 4 built-on gigabit ports. That's the only one. That gigabit ports only allow for 5 to 10 gigabits per second of total bandwidth, with performance of 4 to 8 mega packets per second. Versus if we start looking at the larger 4 or 6U, we're looking at almost gigabit speeds, and again about 8 to 16 plus mega packets per second. That's millions of packets per second. Interesting thing here is they actually do the smaller portions of the spectrum. They're under the CSRs, but I mean, again, these aren't $500,000 routers. These are fairly cheaper routers. Last time I looked at an ASR, we're talking a few tens of thousands. I mean, we're not talking hundreds of thousands. They also can allow for lower speeds, though normally the entry-level ASR is made for at least 5 gigabit connections, or at least an OC line. Some of them come with a 10 gigabit interface card, so you have to take that into mind as well. So how exactly does this work? Pretty much like all the other devices, it has inline cards, and the inline cards vary. Here they are, being our different types of cards, different programmable controllers at the very bottom via USB. Then we have our SIP card at the very top. What I really liked was the modular power supplies, and here they don't actually show the controller planes. These are our SPAs. It's just a different add-on card depending on the peripherals that you need. That's a really big thing with the Cisco routers, is they're very modular. You only pay for the add-on card that you need. Again, we have our 4 gigabit mini FSPs or GBIC slots. Normally that's going to be a Cisco GBIC to fiber. It doesn't have to be. They also have built-on gigabit ports as well. Here, these are normally also allows for 10 gigabit GBICs. Just depends on the unit that you're getting. This was a first generation ASR router. It has a very slow 1.5 gigahertz power PC processor. It has normally 4 gigs of main memory, USB for bulk storage. It has a traditional typical hard drive. Newer ones are coming with SSDs for power performance. It normally has specific interface cards depending on the model that you are purchasing. We have our console, our auxiliary, which is very common. We have our USB, which is pretty typical. We have our management Ethernet, which is different from our data portion Ethernet. And then we have just the faceplate LED indicators. Again, pretty straightforward. It all kind of depends on the items that you need. The interesting thing that they did was the QuantumFlow processor, the QFPs. This is the first generation, and all this really did was it allowed for multi-core plus traffic manager to do better flow control. Here's the physical board. again, when you go through it, you can see that they're clearly labeled, which is the CPU, the crypto engine, our CAMs, our ASIC processors, our memory, our storage. Honestly, I've never really had a reason to know specifically what each component really is. If you're using these off the top of your head, normally you're also having a manual, so if you see damage or something, you can kind of see exactly where it's at. That's been a big thing. So, where do these guys actually sit? They actually sit on a very small backplane. And they have the appropriate lights that you need to be aware of. But again, when you're working with these, normally you're going to have a manual, because you're not going to memorize all of the light codes. That's a big thing here, is you don't memorize all the light codes. You do need to know the number of processors, their speed, its throughput, its buffer, its cam size. You also need to think about is it going to be able to meet your need. For example, the big thing here is between our 5 gigabit and 10 gigabit per second is our crypto bandwidth. We're looking at 3 times the bandwidth for our AS1000 ESP10, which is, yes, it's a 10 gigabit connection, but for our throughput for our cryptology, it's 3 gigabits per second. The newer ESP20 does do 8 gigabits a second, but I was unable to find any solid details on it. They had one set of processors initially, but because of performance issues, they did work for better processors. Now they have better processors, again, more efficient, better power consumption, pretty standard, a 10 gigabit aggregated performance per inline card. But how does this all work together? So we have that mid plane, or our back plane, and we have all of our subsystems connecting to it, and also interconnecting with one another. That's been a huge area. Each of our add-on SPA port add-on slots, we have a direct connection between our server processors, our services processors, also dealing with our QFP subsystems for memory control. All goes back to just faster connection. That's the big thing here, is long-term, stable, fast connections. Interesting thing with this type of device was we're starting to finally look at a transition away from iOS to iOS XE, XR, NX. We're looking at the new generations of operating system for the Cisco devices, because they're starting to realize that iOS just has a lot of shortcomings. Better control is one of the main advantages of our iOS X. So now that we have at least a basic understanding of it, we can look at a little bit more of the innovation of it. With heavy engineers, part of the QFP, the QuantumFlow processor, on top of that, with the time investment and the patents, you actually end up with the CFP that does well. And you see that type of technology used in later routers. A big part of that deals with the ability to process millions, if not trillions, of packets per second at an unbelievable rate, and that's because of the way the QFP functions. It also allows for better availability, scaling QoS, and that also is reducing error and better efficiency management. So how does the control and forwarding plane actually work? A big thing here is it depends on the model that we're looking at, because within our iOS XE we have our router protocols that are either active-active, active-standby, standby-standby. It just kind of depends on what we're going for. If we're looking for zero packet loss, we'll see an iOS and an active standby for both our RP and our ESP. If our RP was active and our ESP was active, we could see some packet loss. And we'll slowly see them transition down to an orange state, and that actually is traffic interruptions. Interesting thing here is this is the first iOS that comes out with software virtualization, allowing for virtualization of router and switch ports on the devices. They transition to additional chassis and devices after this, but our ASR 1000s were the first major one. So now we have our chassis, control planes, and data/service planes, and depending as our needs grow and change, we have different protections for it. Interesting enough here is they're flexible. It really just depends on your needs, and that's one big thing that just is hit on over and over and over, is it's the flexibility. Last is our enterprise solution application. It's scalable. That's the thing we have to take away from this, is if we're doing this via a MPLS network, or even through our DM VPNs, is it's scalable. It's fast. It allows for, they say 10,000 IPsec tunnels at one given moment, which is normally 50 trillion packets per second. Normally roughly the 3 gigabits per second for our encryption plus our bandwidth. That's also including our 7 gigabits per second, assuming no crypto bandwidth. And then you have your different types of methodologies to actually do your encryption. What gets interesting here though is backup connections. Is they allow for distributed load between multiple routers, and that also includes multiple pathways back to our core routers. The IPsec tunnels, I've read numerous articles on this. They say 10K, but I've seen some that only topped out at 8, and I've seen some that went to almost 15. Same series, same model, same licensing. It was just kind of depending on the situation and the stability of the ISP in your area. That's something that you have to think about. Keys to our ASR 1000 is our forwarding. Big part of that is our forwarding. How does it all function together? That includes our hardware, our flexible architecture. That includes our bandwidth and our throughput, processes and queues, and then just the overall development of our QFPs. Our ASRs are mid-grade, keeping in mind that our CRSs are our higher end grade. Things to remember, regardless if it's an ASR or a CRS, is these devices are made to be, first of all, high performance, high available, and very efficient. Efficiency among everything else. Okay, so our last slide, I figured I would talk about expectations and assignments. One of the big things here that I'm looking for is just a basic evidence that you at least understand what we're talking about. Backed by support within the literature. Everything goes back to our literature. That's one key thing that we keep taking for granted. If you say QoS is important, why? Find an article on why QoS is important. Preferably scholarly literature. You can actually access our library system, and we have a great amount of resources within our library system. Or you can even ask one of the librarians through AIU to help. And that's another large item, is don't underestimate the importance of our librarians. But you'll be able to find current literature on a lot of these major topics because they are of interest. But the only thing it does is add credibility to your paper. When I go through it, first thing I'm looking for is when you make a claim, are you providing evidence to back up your claim? First and foremost, that's the first thing that I look for. Once I see that there is a pattern of claim and support or backing by evidence, then I start looking at things like formatting and structure. But if I don't see paragraphs that are being supported by literature, automatically I start just thinking how this paper was taken away. The argument of, well, I didn't use any resources. That's not always a good argument. The argument should be, here's my claim, here's the evidence that I've found supporting my claim. It is not just me making this statement, it's the literature, it's the current body of knowledge within this area. Bam. The reason I say that was the best way is because there is no questioning. Because it's not just your word, it's not just you. It's the literature, which has already been shown to be true. So you have to keep that in mind. That's it for our week 2 lecture. Next week we'll be going over chapters 9, 10, and 11. And that's going to be mainly focused on our iOS, XR, and QoS. Thank you, and hope you guys have a great day. Bye.